All right, guys, so this is a video explanation for your homework task. So first of all, we're going to watch this video, and then this will lead us to some practice examples, and then you should be able to do your homework accordingly. But I need you to study this first. So let's start.
What we're going to do in this video is think about different ways to represent how position can change over time. So one of the more basic ways is through a table. For example, right over here, in the left column I have time, maybe it's in seconds, and in the right column I have position. And this could be in some units, let's say it's in meters.
Notice that there is a negative reading now. Because there is a negative value, then this is a displacement. Okay, it's not a distance anymore because now I'm describing direction. So the fact now that I have a negative value means that I am considering directions. So let's have a look at this. How would this look like on a displacement time graph? And because displacement is represented on the y-axis, I'm going to have a negative position and a positive position. So I'm going to have a positive y-axis and a negative y-axis. And therefore, my graph is going to go above and below the x-axis. We'll see now what that means.
So at time 0, we're at 3. After 1 second, we are still at 3. After 2 seconds, we're at -1. Then after 3 seconds, we're at 0. After 4 seconds, we're at 0. Still at 0. After 5 seconds, we are at 2, maybe 2 meters. Now, this is somewhat useful, but it's a little bit difficult to visualize. And it also doesn't tell us what's happening in between these moments. What's happening at time half of a second? Did we just not move? Did our position just not change? Or did it change and then it got back to where it originally was after 1 second? We don't know when we look at a table like this. But another way to think about it would be some type of animation. For example, let's say we have our number line, and let's say the object that's moving is a lemon. And so at time 0, it starts at position 3, so that's where it is right now. And let's see if we can animate it. I'm just going to try to count off 5 seconds and move the lemon accordingly to what we see on this position time table or time position table. 0, 1, 2, 3, 4, 5. So that was somewhat useful. But maybe an even more useful thing would be to graph this somehow so that we don't have to keep looking at animation, so that we can just look at, with our eyes, what happens over time. So for that, we can construct what's known as a position time graph. Typically, time is on your horizontal axis and position is on your vertical axis. So let's think about this a little bit. So time equals 0, our position is at 3.
This is what I mean by having your y-axis being positive and negative. This is now a displacement time graph. So I need you to be sketching this, and I need you to be taking notes that this is called for the title. This is, yes, a position time graph, but it's of the displacement type, okay? So you need to put this on as your title.
So at time 0, our position is at 3. And then at time equal 1, we're at 3 again. At time 2, we are at -1. At time 2, our position is -1. At time 3, our position is 0. So our position is 0. Remember, even though we're thinking about left-right here, position is up-down. So here, our position is
very important. Left, right here. However, here we are using the axes. We're just going like 3 and 0. It's all on the axis here. It's 3 on the 3 on the x-axis and 0 on the y. So it's just going to be exactly on the x-axis. But for 2, it's 2, 2, and -1. So I have to go one step down.
Is 0 at time 3. And then at time 4, our position is still 0. And then at time 5, our position is at 2. Our position is at 2. So for the first second, I don't have a change in position, or at least that's what I assumed when I animated the lemon. And then as I go from the first second to the second second, my position went from 3 to -1, from 3 to -1. And if we do that at a constant rate, we would have a line that looks something like this. That's supposed to be a straight line. And then from time 2 to 3, we go from position -1 to 0, from -1 to 0. Here, it would have been going from -1 to 0, moving 1 to the right. But over here, since we're plotting our position on the vertical axis, it looks like we went up. But this is really just going from position -1 to position 0 from time 2 seconds to 3 seconds.
What would help you is actually plot it yourself, like sketch it yourself to understand what's going on.
Now from 3 to 4, at least the way I depicted it, our position does not change. And then from time 4 to 5, our position goes from 0 to 2. From 0 to 2. And so what I have constructed here is known as a position time graph. And from this, without an animation, you can immediately get an understanding of how the thing's position has changed over time. So let's do the animation one more time and just try to follow along on the position time graph. And maybe I'll slow it down a little bit. So over the first second, we're going to be stationary. So we could just count off 1 Mississippi. And then our position goes to -1 over the next second. So then we would go 2 Mississippi. And then we would go 3 Mississippi, 4 Mississippi, and then 5 Mississippi. But hopefully you get an appreciation that this is just a way of immediately glancing and seeing what's happening.
Okay.
What we're going to do in this video is think of 1 over the next second. So then we would go...
Okay, so forget about the Mississippi thing. Let me just explain this to you. Here, he is moving at a constant speed he is stationary. He is stationary, not constant speed. He is stationary for 1 second. Then he moves then he moves back to the -1 position at a constant speed. You see that? At a constant speed. Now, if you want to find the value of that constant speed, you would need to find the slope. So he moves from the 3 all the way back in the opposite direction to the -1 position. You have to say the direction now. And if we ask you how much time it took 1 second to do it, because I'm looking on the x-axis over here. And he covers a distance. If I want to see the distance, I'm going to have to see the difference in the distance on the y-axis. So he goes from 3, that's 3 to 0, and then a -1, so he covers 4. So I'll show you more on the example that we have in the PowerPoint. But just to give you an idea, I just talked about the distance, the time, and the speed. Then he also now moves at a constant speed from the -1 position back to the origin, and he takes 1 second for that. Then he stops for 1 second where he is at the origin. I talked about speed, distance, and time. Now he moves from the origin back 2 meters in the positive direction, and that takes him 1 second. To calculate the speed, I would divide the change in the y divided by the change in the x. So you have to take each section and find its speed separately. So 3 things you need to consider. You need to tell me what's happening to the speed and calculate the speed by delta d over delta t. And then you have to tell me where is it and where is it going, and the final position, yani initial position and final position, the time it took to travel, and the distance it covers. So let's have a look over here. New share. I'm going to go back to the PowerPoint. It's this one. Okay. Right. So it's just give me 1 second here. So things that you need to include when you are describing the shape of the graph. So when you describe the shape of the position time graph, here are the things that I'm looking for, okay? Number one, you have to tell me, you have to describe the speed, okay? And by that, you're gonna say either it's constant or it's 0 or slows down or speeds up. Now, when it's constant, it's going to be a straight line, and if it's 0, then it's going to be a horizontal line. Any horizontal line, doesn't matter where it is, horizontal line anywhere. When it slows down, it's going to be a curve, and speeds up also a curve. Now, you're going to tell me something about the speed in words. So you're going to describe the speed in words. And then you're going to say, you're going to calculate the speed if it is constant. Then you're going to have to give the initial location. For example, you're going to say it moves from, and then you give me that location. And that location, you have to tell me if it's a positive or negative location, or if how far is it from the origin? Okay, like 3 meters above the origin, below the origin, or to the east, west, positive direction, negative direction. The question will help you indicate where, okay? And then you have to say in which direction it is moving, like towards the negative, positive, and then locate and specify the final position, like where does it end up. So it's like -1 meter, at -1 meter, meaning it's 1 meter to the left of the x-axis, to the left of the origin, let's say, whatever. Yeah, whatever the question is specifying. Then you have to say the time it took to make this motion. Okay, these are the things that I'm looking for when I ask you to describe the motion. So make a note of these and always check against them. Okay, so let's apply these ideas for question number 11. Okay, I'm just gonna insert here a place for me to write on, and I'm just gonna put a shape over here and cover the other questions so I can write in that space. Okay, so it says here in figure 12, I need to describe the motion in words. Okay, so first of all, moves an object. It's a car. So car moves at a constant speed. Why? Because it's a straight line. That's number one. Number two, the car, and I can calculate the speed. This speed is equal to the gradient, the slope. So I'm going to take my initial position, my final position, and the difference in the time. So I need my delta D over delta T. Now this is, so now my speed is equal to, I put it on another line. So my speed is equal to my final position, which would be -55 over here. So -55, here it's -55. Okay. And it's on 7.5. These are the coordinates. So these are seconds and these are meters. That's seconds, not a 5. And here you have 0 for the x and 125 for the y. So that's meters and that's seconds. So minus 55 minus 125 over the time, which is the final time, which is 7.5 minus 0. And I'm going to have to put meters at the top because I take marks for that, and seconds at the bottom. And then your final answer would be the calculated value that you get in meters per second. I'm not going to calculate it, you do. Okay. So you put your speed value. So speed, the constant speed is going to be in so-and-so in value in meters per second. It's going to be a negative value. Negative value only means that it's moving in the opposite direction. Okay. So when you get a negative value, it means that it's moving in the opposite direction. Number 3, you would say that it moved for the distance now, it moved, or the location, moved from 125 above, or in the positive direction above origin, to which point? Minus 55, which is below the origin. And that it took, number 4, it took how long? It took 7.5 seconds. You would see that you're actually, when you describe the motion, you're actually like looking at the delta D and the delta T. So basically over here, I'm doing my delta D, and over here, I'm talking about my delta T. But I'm being more specific about where it was. I'm talking about the D initial and the D final. So I'm specifying D initial, D final, and that change in the time. Okay. Now, next question. So we're not going to do question 12. For now, question 12 will come later, so 12 is not necessary. We're going to do 13. Answer the following questions about the car's motion. Assume that the positive x direction is east of the origin and the negative is west of the origin. At what time was the car's position 25 meters east of the origin? Okay. So we're still looking at figure 12, okay? So car's position 25, okay, so they said that positive is east, so that is supposed to be east. And below the origin is west. So where was it 25 meters east? So 25 meters, it was over here. So what time, sorry? So what time, I'm just going to go horizontally, hit the graph, and then read this value over here. I'm assuming it's 4.0 because it's not it's not a good graph because there's no grid lines. So I'm just saying here it's 4.5 seconds. I'm just assuming. Now, where was the car at 1 second? 1 second. I'm going to go up, hit the graph, and go horizontally. It's at 100 meters. Now, what was the displacement of the car between 1 second and 3 seconds? Okay, 1 second and 3 seconds. So the displacement is the difference in the locations. So here, what was this value? It was 50. And that value, we got it as 100. So it's the difference between, that's going to be D final, and that's going to be D initial. So it's going to be minus 50. Why? Because your final was at 50. Your initial was at 100. So you're going to say 50 minus 100 is equal to minus 50. This only means that he is covering 50 meters towards the west. So this means 50 meters from east to west. Okay. the graph in figure 13 represents the motion of two pedestrians, يعني ناس بتمشي بالشارع, some people walking, who are walking along a straight sidewalk in the city. Describe in words the motion of the pedestrians. Assume that the positive direction is east of the origin. So that's east. Now, so if we were to describe this, I would say that pedestrian B, I would say pause the video and try to solve this on your own, just to check later. So he starts in the positives. Because I don't have values, I would just give an overall general description. I would say he starts east. He starts east of the origin, okay? He starts east of the origin, and he moves at a constant speed for some time. We don't know what the some time is, but for the same amount of time as A, that's one way to say it, and he reaches point B, which is east of the origin. However, for A, he starts below the origin, meaning he starts at west of the origin, and he moves at a constant speed within the same amount of time and ends up east of the origin. So he starts at west, he finishes at east because he is above the origin. So that's one way of describing his motion. And he is also moving at a constant speed. I know that because it's a straight line now. Now, Ari walked down the hall at school from cafeteria to the band room, a distance of 100 meters. So he walks from the cafeteria to the band room, so cafeteria and band room, and he covers a distance of 100 meters. And a class of physics students recorded and graphed his position every 2 seconds, noting that he moved 2.6 meters every 2 seconds, meaning that this is his speed. He was moving at a constant speed, just like the buggy car. So the speed is equal to delta D over delta T. And he was able to cover 2.6 meters for every 2.0 seconds. This means that he covered 1.3 meters for every second. That was his constant speed. The question is asking, when was Ari at the following positions? When, yani time. So what time was he? When he was 25 meters from the cafeteria. Where is 25 meters? That's the cafeteria. So 25 meters over here. That's 25 meters. So what time was that? Now, by that, we want the T final. Okay, we can say now that since the speed was constant, I can use this value. Now, the speed is constant. I'm going to go to the top now. I'm going to do part A at the top. The speed is constant. When the speed is constant, this means that it's going to be always 1.3. And it's going to be for whichever delta D and delta T I have. So if I take my final position to be 25, as they're saying, and my initial position in reference to the cafeteria is 0, and I need to find my T final, and my T initial is 0, so that really this can just go, like the minus 0 can go. So this becomes 1.3 equals 25 meters over T, and here this is meters per second. To get my time, that's going to be cross multiplication. I take the T next to the 1.3, and then I divide the 25 by 1.3. I'll teach you more about this in class. It becomes 25. This is a math thing, okay? If you don't know, I'll help you more in class. Divided by 1.3 meters per second. So this means that I was able to find my time from the gradient or from the slope because it was always constant. So I rearranged my equation. When it's 25 meters from the band room, okay, where's the band room? If I say it's 25 meters in that direction, This means in total from the origin, this is a 75. So if it's a 25, how did I know it's 75? Because 100 minus 25 is 75. So that's that location. If that's 100 at the end at point B, then this is a 75. So I'm going to exactly do the same. I'm going to, for part B, I'm going to do the same. I will say that 1.3, but now my final position is 75. And I'm going to take my initial location as 0 meters. And I will divide it by my time, which is t that I don't know. Mine is 0, so that doesn't really matter. Now I need to find my time. So 1.3 is equal to 75. Now I'm going to have to put here meters per second. I'm going to have to put here meters. And I'm going to have to put here t. To rearrange this, I have to cross multiply. It's like t times 1.3 equals 75. To get my 75, sorry, to get my time, I will need to divide both sides by 1.3. So this one goes away. So therefore, my time is going to be equal to 75 over 1.3. And that would be here meters, and that's meters per second. So when they cross out and set 1 divided by 1 over second, this will give you your value in seconds. So that was a challenge question. So that's why it's a little bit more complicated. To create a graph, you're going to have to take coordinates and try to do this on your own for like time and speed, time and distance, and try to sketch it. Anyway, so this would be the rest of what you need to be looking at. So basically what I need you to do after you study what I've just explained to you, I need you to look at the meaning of multiple objects on a position time graph. This is how multiple objects look like. Okay, there's an example here, and you can explain its shape over here by also checking the explanation, because it's a worked example, and then you can see how velocity is being worked out. This is just repetition for you, how to find the slope. So you've already done that with me in class, and that's the equation to find the slope. They're just using x over here. I use d, but x is the same because it's moving on the x-axis. And then this is a worked example that you can try to look at. Then there's another example that you can look at for calculating the velocity and average speed. So look at that, please. And then I need you to solve these questions. Okay. Be careful when if they're asking about the average velocity, make sure that you put your method. Okay. That you put your method. You show me how you calculated it, and you also show me how you show the units. Okay. So it's all very easy. It's all about like calculating speed and velocity, but I need you to include your method and your units. And then I will ask you to upload it on Al-Khazne. I'll see what you did over there, and then I'll ask you to improve it, okay? If need be. All right. So this is one way to test your understanding. It's not going to be difficult. And I don't need you to do question 32, sorry. You don't have to do that. Yeah, so you have to do 27, 28, 29, 30, and 31. The rest of the slides are just to review for you, okay?